two numbers whose difference is 24. How do I write that? So these are any two generic numbers whose distance, I don't know why distance, it comes to my mind, whose difference is 24. Good. So that was clear. That was established. We found two numbers, unknown numbers, of course. We don't have them yet, but we know that the difference is 24. Excellent. Find a pair with the minimum product. So we want the minimum product. But I don't have the product. Can anyone tell us how to write the product of these two numbers? One number is x, the other one is y. How do I write their product? That's it. Their product is x times y by definition, right? So if I have 2 and 5, what is the product of 2 and 5? 10. If I have 5 and negative 3, what is the product of these numbers? Negative 15. So if I have x and y, what is the product of x and y? xy. Good. So, however, I'm having a difficulty here, and here's the difficulty. This is the variable, this is the dependent variable, and these are two independent variables. This is not a function. This is the function. The product of those two numbers is a function. So do not confuse this y with f of x. Okay, so next. Look at this equation, because I would love to be able to eliminate y. I want to replace y from this equation by something. So I can have only a function, p of x, of one variable. I can have two variables in a function. Not in this class. In other classes, yes. But not in this class. So, but I'm given a condition. I'm given an equation. Can I solve this equation for y and then plug the answer in here? So how do I solve this equation for y? We know how. We've done that before. Yes. So I have x minus y equals 24. I subtract x from both sides. And now what? I haven't finished solving for y, so I have y equals. Very good. Okay, this is what I'm going to do next. I'm going to replace y in the function called product by what? That's it. So now I can say with confidence that p is a function of only x, nothing else, with x gets copied, and in parentheses x minus 24. Of course, I will distribute. And you can say, why are you doing all this? Well, I cannot determine the minimum of a function if I don't have the function. I'm asked to find the minimum product. How can I find the minimum if I don't have the product? So that's my starting point. I have to write the product. It's obviously the product of these two numbers, so it's x times y. Now I run into some difficulty. What is the difficulty? Well, I have the dependent variable, but I also have two independent variables. I can't do that. So from here I solve for y, which I did. Y equals x minus 24. And I replace y by x minus 24. And now I will say, I'm happy. And you can say, why are you happy? Because I have the function. I have the function that is the product. And now I can find its minimum. But does it have a minimum? And first of all, what type of function is it? It's quadratic. Second question, does it have a minimum? Because the leading coefficient is positive. It has a minimum. Now the next question, question number 3. How do I determine the minimum? Say it again. No, the x-intercept of the parabola will never be the minimum unless the vertex is on the x-axis. How do I determine the minimum of this function? What do I have to calculate? Exactly. Which means I have to start with, which is of course the same thing. They're all the same. So negative, then b is negative 24. 2 times a is 2, so this is 12. So I determined x. If x is 12, how much is y? But this y is not this y. This is p of 12. This number here that I did not determine yet is p of 12. But I'm talking about the other number. I determined the first number, 12. How much is the other number, which is denoted by y? Very good. Thank you very much. And now I'm going to ask what is the product. If I have the numbers, I don't have to go back and plug it in. I have 12 times negative 12, which is negative 144. You can go back and plug in, but I guarantee you, you'll determine the same exact 144 negative. So let me show you. So we have 12 squared, and then minus 24 times 12. And here it is. Because that's how we determine the product. Multiply, yes?
So to find the y, you plug in 12 for x.
That's what we always do for the vertex, for any point. So if I have x, this is f of x. I have 12 for this function. So this number is p of 12, and we just plugged it in to get negative 144. Another option is I already determined x, this x, and if I determine this y, if I have 12 times negative 12, the product is negative 144. Any questions? Any questions? Please bring any question from my lab's math to class, because there is no way we can spend the entire time on everything. But I'll be more than happy to see whatever you encounter. Any questions about these problems? They're pretty much all the same word problems. They're asking us to find the y-intercept, the vertex, in other words, max or min, and where and I didn't even realize that I had a ball here. Could use it. Where it hits the ground. Okay? Any questions? So here's how I will write the answer. The product, the minimum, because that's what we were asked to do. The minimum, determine the minimum product of two numbers whose difference is 24, comma, is negative 144. The numbers are, can anyone give us the numbers? The numbers are 12 and negative 12. And the minimum product is 144. Any questions? Any questions? Okay, let's start. Section 3.2 requires time. The first problem, it will take me like forever. It will seem like it. But then the second one will take us 5 minutes, and then the third one will take us 2 minutes. But the first one will take like forever. So 3.2, polynomial functions. Okay, and you can say, what about linear? and quadratic. Aren't they polynomials? Yes, but these were done. We're not really talking about linear and quadratic here. We are talking about degree 3, 4, 5, 6, 7, 8, etc. We're not talking about degree 1. We're not talking about degree 2. We're starting with degree 3, 4, 5, 6, etc. Well, obviously, we have two different types of degrees. What are these? Degrees that are what? Exactly, they're odd. And what are these? Degrees that are even degree. We're not talking about the function being even or odd. We're only saying that its degree is an odd number or an even number. So basically there are two categories. And let's start with the odd degree and then move on to the even degree, or vice versa, it doesn't matter. So I would like to create a table. On the left-hand side, odd degree. On the right-hand side, even degree. Before we even look at a polynomial function degree 3, 5, 7, or even degree 4, 5, 4 6, 8, I have to present some preliminaries, things that we have not discussed before when we graphed other functions. And before we clear these and understand these pieces, then we can put together everything and graph polynomial functions. It will be hopefully very easy for you if you follow with me step by step. Can you give me a function that we know everything about and it has odd degree? Yes, we don't know these. Perfect. Yes, cube root is fine. Not the cube root, but the cubic. Yes. No, I'm talking about something that we know absolutely everything about. It's an odd degree. It's polynomial. And it has two possibilities, correct? It has this possibility. And it has this possibility, correct? What is the leading coefficient here and what is the leading coefficient here? Excellent. Increasing from left to right, the leading coefficient is positive. Decreasing from left to right, the leading coefficient is excellent. So can I say then, stay with me for a moment, please. Can I say then that this is coming from negative infinity and going to positive infinity? What can I say for the other one?
Going from positive.
Decreasing to negative infinity. Every odd degree, any polynomial of odd degree, degree 3, 5, 7, any odd degree will behave in the same way. What do I mean by that? If the leading coefficient is positive, it will start at negative infinity and go to positive infinity. Any odd degree with a positive leading coefficient. Any odd degree with a negative leading coefficient will do what? Exactly. So any odd degree will have this end behavior, which it's called end behavior. So any odd degree, degree 3, 5, 7, if it has a positive leading coefficient, will behave like this. If it has a negative leading coefficient, it will behave like this. It will not look like a linear function. No, not at all. But it will start at negative infinity and go to positive infinity. Or in the case of a negative leading coefficient, it will start at positive infinity and go to negative infinity. Can anyone give us the simplest possible even function, even degree function, polynomial, of course, that we know absolutely everything about? Because we just finished it 5 minutes ago. Quadratic. So what are the possibilities for quadratic? Either, exactly, coming from and going back to, or coming from and going back to. That's exactly what all even degree polynomial functions will do. So it's either this or this, which means this or this. What is the leading coefficient here? Indeed. Well done. What is the leading coefficient here? We just finished that. Indeed. So this is the end behavior. This is the end behavior for any even degree. So if I say degree 8 and the positive leading coefficient, what will you say? Degree 8 and positive leading coefficient. I give you the options. 1, 2, 3, 4. Exactly. Even degree, positive leading coefficient. Okay? Odd degree, negative leading coefficient. 1, 2, 3, 4. Odd degree, negative leading coefficient. From what? From 2? There are 3 pages in the book about just this topic. There is no mean. Okay, so we cleared end behavior. Do I still have time? Yes, a few minutes. We have never talked about end behavior up until now. Okay, here's the next one. Multiplicities of X-intercepts. There's a C in there, sorry.
This is still 3.2, right?
Everything is, yes, but I said it will take forever.
Okay. I was thinking
Till I go through all the topics and everything that I need to present before we even look at the first example. I warned you.
I was just making sure for my notes.
Yes, yes. Sorry about that. It will take forever. Sorry. Okay. So let me give you a few examples. And you'll understand what we are talking about here. Multiplicities of X-intercepts. Now let's say I have x minus 1 to the 4th equals 0. And let's say I have x cubed equals 0. Not connected. Don't look at the second one just yet. Let's look at the first one. How many solutions does this equation have? 4. The degree is 4. And all of them are what? Indeed, 4 solutions. But all of them are x equals. It's x minus 1 times x minus 1 times x minus 1 times x minus 1. So then all of them are 1. Very good. Multiplicity equals 4. So this equation has 4 solutions, 4 x-intercepts. This function has 4 x-intercepts. And because it appears 4 times, multiplicity of 1 is 4. Let's look at the other one. How many solutions will this one have? I'm still looking for the x-intercepts. This is a function. I set it equal to 0. I'm looking for x-intercepts. So how many x-intercepts will this have? What is the degree? So it has to have 3. But it happens that all of them are the same, and they are equal to perfect. So the multiplicity of this x-intercept, which is x equals 0, is 3, of course. Okay, one more example, and then I'll explain what this means about the graph of the function. So let's say I have this function, and I set it equal to 0. X minus 2 squared, x plus 3. Sorry, to the 3rd equals 0. What is the degree now? What is the degree of this? What is the degree of this? What is the degree of this? How much is degree 1 times degree 2 times degree 3? 6. How many solutions will you give? Excellent, wonderful, well done. So please tell me the solutions. Multiplicity? It appears only once. Very good. Next, x equals 2. Multiplicity? Very good. And the last one, multiplicity? 3. The multiplicity has to equal the degree. Multiplicity 1, multiplicity 2, multiplicity 3. Does that equal degree 6? Yes. Okay, we understand now what multiplicities represent. The number of times the solution appears. Here x equals 0 appears once, multiplicity 1. Here it appears twice because of the power, so multiplicity 2. Here x equals negative 3 appears 3 times, multiplicity 3. Okay, so what is so important about it? Okay, now here is the result, or the final explanation about multiplicities. So I'm going to graph a few situations. So I graphed 1, 2, 3, 4, 5 functions. Let's start with this one, because we know everything about it. So can you please tell me how many x-intercepts does this one have? True, but they're two the same. So then this x value, let's say 15 or 10 or 7, it doesn't matter, has multiplicity? Exactly. So it's a turn. The function turns at that point. Now, by comparison, how many x-intercepts we consider that this function has here? Look at this. This is just a quick turn. This one is slow, 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 and finally turns. What is the multiplicity? It cannot be 2. And it cannot be odd. Exactly. So it's a turn, but it's flat. Good. How many solutions do you think this one has? This is linear. It's a linear equation. How many solutions can it have? 1. So here, this point or this x-intercept has multiplicity. Say it louder. Of course. Absolutely. Let's see this one. Is it the same? Of course not, right? So this one takes its time. Yes, okay. Slowly, slow. It doesn't mean that it crosses 3 times. No, but it gets closer and closer and still closer and closer and closer. Okay, finally it crosses. And then away from it, away, slowly, 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 away from it. What do you think the multiplicity here is? It has to be odd. If it crosses the x-axis, it must be odd. If it turns, the multiplicity must be even. So is it the same? Exactly 3. That is multiplicity 3. Like this one. If you remember when we graphed x cubed, let me refresh your memory. We graphed x cubed many times. Here was x cubed. I never graphed x cubed like that. Why? Because x cubed has 3 solutions. X equals 0. Multiplicity 3. So it takes its time. Finally, what do you think this one? By comparison to this one? So this is slow, but this is way slower. Exactly. Multiplicity 5. So in short, oh, I'm sorry. If this